Hello, navigators. Welcome to the lesson library of celestial navigation, illustrated and animated. I'm Graham Peterson. This is lesson number 11, and in this video we're going to go over how we use publication 249 site reduction tables to determine the intercept and azimuth. So let's get started. This is the worksheet that we use. Notice you can use it for either publication 249 or 229. So we're going to use this worksheet in conjunction with this problem. This is going to be our example. It's the Celestial Navigation Challenge problem of January 2021 called Terra Nova and Scott of the Antarctic. If you want the details, the background, the narrative, and the complete solution work set of this problem, you can go to this website. That's the Sarasota Power Squadron's website, sarasota-boating.org/celestial-navigation-challenge. And from this information, we are going to use the law of cosine worksheet, which is part of the solution set. And from this worksheet, we're going to extract this information, the latitude, longitude, declination, HO, and the total GHA. And then we're going to insert it right here in block number 1. This is how easy this is going to be. We're going to input this information by the numbers 1, 2, 3, 4, 5, and 6. This lower left-hand block, just forget about that. That has to do with publication 229, and we're not going to be using that in this example. So let's just get started. Let's enter this data into the worksheet. Latitude, longitude, declination, HO, and total GHA. So now we're ready to go. Block number 2, these are the values that we need, or the arguments that we need to enter the tables. Now this is A latitude, means assumed latitude. A LHA means assumed LHA. Anytime you use tables, whether they're for publication 249 or 229, or even the site reduction tables that are in the Nautical Almanac, we have to enter these values as an even number. It's very important. That means no minutes. No minutes. So to do that, what do we change the latitude to make an assumed latitude? Well, this is super easy. All you do is just round the DR latitude down or up. If it's 30 minutes or less, you round it down. If it's 30 minutes or more, you round it up. This case, it's 18 minutes, so we round it down to 5 minutes, or to 5 degrees south. The declination you simply enter from your entry data as is. Notice this does include the numbers, or the minutes. Also notice that the hemisphere for the latitude and declination are the same. And we want to make a note of this because this is very important. When we go into the tables, we have to identify each page is listed as contrary or the same. As far as the latitude and the declination are contrary or the same. In this case, they're the same, so we're just going to circle same. If they were different, then we would circle contrary. Now let's go down to the LHA. How do we do the assumed LHA and get it with no minutes? See block 3, so we'll just take that uncertainty over here to block 3. And we're going to import the GHA from our entry data. And we know that to get the LHA, we're going to have to either subtract or add the longitude based upon whether it's in the eastern or western hemisphere. We also know that the LHA has to have 0 numbers because that's an assumed LHA. That's what that means. That has to be 0. So we have a western hemisphere, which means we're going to be subtracting our DR longitude. So let's just bring over the DR longitude and see what we have to do to make all these parameters valid. Well, we can subtract 15 from 47, that's easy. We can't subtract 12 from 3 and get 0, so we have to just make a change here on our DR longitude. So we're going to change the 12 to 3.9, just that simple. So now we can subtract it and we get 0, and we have a different number for our longitude. That's why it's called the assumed longitude. It's different. Now, is this the correct LHA? We need to check that because look at this rule, the resulting assumed longitude must be 30 minutes or less from the DR longitude over here. So we just find the difference to make sure it's 30 minutes or less. In this case, it's very much less, so we don't have to worry about it. This is a good number, so that means our assumed LHA is good. We'll just put that in the assumed LHA box. Now we have all of the arguments to go into the tables. So the next thing we want to do is go to block 4. First thing, let's just identify which tables we're using for future reference, so we'll know where we get this data. But before we actually enter the tables, I'm going to step back a second to block 3 and give you a couple more examples on how we can use, how we can calculate the LHA for your future reference. You'll probably run across different situations. Okay, we're going to use a different set of examples, so this is not the same as our Terra Nova question. So let's set up our formula over here. We have the total GHA, 23 degrees, 42.7. West, it's a western longitude, so we're going to be subtracting. We bring over our DR longitude, and then we just subtract. This is minus 37, so we need to adjust that to make sure it's a valid angle, which means we just add 360 in this case and recalculate it, so we'll get 323 degrees. That looks good. Obviously we can't subtract 10 from 42 and get 0. We have to change this just like we did in the previous example. So we're going to make that the same minutes as the GHA. That way when you subtract it, it's 0. But we have to check to make sure we're 30 minutes or less difference in our longitude and our assumed longitude. Here's the difference, 32.7. In this case, that's too much, which means that's wrong. We got to change something. We need to go back to the assumed longitude and change something. So let's take this structure and put it again over here. So what we're going to do, we're basically going to take a degree off of the 60 degrees and make that 59. 59 recalculated at minus 36 instead of minus 37, adjusted to make it a valid number, and so we've got 324 degrees. 42.7 minus 42.7, that's good. So let's check this one. Get the difference in the DR longitude and assumed longitude is 27.3. That's less than 30, so that's a good number. So now we're going to stick it in there, and so that's valid. So all we did was just adjust it for a negative degrees. Let's take one more example. We're going to use an eastern hemisphere for our longitude. Exactly the same numbers, except we're going to flip the boat over to the eastern hemisphere. Set up our formula illustration here. So it's the eastern hemisphere, which means we add the DR longitude. DR longitude is 60 degrees, 10 minutes. We can do the 60 and 23, that's 83 degrees. We can't add 42 and 10 and get 0, so we have to make an adjustment. What do we do to get 0? Well, you can't add two positive numbers and get 0. So we're going to have to change this to something different. We're going to change that to 60 minutes. That way, when that equals 60 minutes, then we can just add that 1 degree on this side to the degree side. So what figure do we use? Well, you just subtract the GHA minutes from 60, and you'll get that difference, which is 17.3. That way, when you add those two, we get 60 minutes. Then we can take that minute, or that 60 minutes, and as a degree, and add it to there. So let's check that. Difference between the assumed longitude and DR longitude is 7.3. That's good. So that's a good number, so we'll stick it in there. So you just have to play with the assumed longitude to make sure those two criteria are met, that the LHA is 0 minutes, and that the assumed longitude is 30 minutes or less from the DR longitude. Just that easy. Do those a few times and you'll have it down pat. No problem. Now let's go back to our worksheet. We want to enter the worksheet. To do that, we need to find, or we want to enter the tables. We need to find the tables. So to do that, we're going to go to the nauticalalmanac.com website. This is the same website that we use when we want to pick out the nautical almanac that we're using for the problem. And this website also has the 229 and 249 tables. Be sure you use this website because there are several different online websites that have nautical almanacs and the tables, and they seem to be off a little bit. Probably not significantly to make a difference in your position, but when we're grading these problems, we want to be on the same page with you guys that are submitting these solutions. So it's just important that we all use the same nautical almanac and all use the same copy, the same version of the tables. So let's go over to the Nautical Almanac website, homepage. We scroll down past this link. This is where you would choose if you're looking for a particular year for your Nautical Almanac. We've already done that for this example, so we're going to scroll down a little bit farther to Site Reduction Tables, 249 and 229. Click on 249. We go over to the volumes. There are 3 volumes, one for stars. Volume 2 and 3 are for sun, moon, planets. Volume 2 goes from 0 to 39 degrees latitude. Volume 3, 40 to 89. In our problem, we have a latitude of 5 degrees south. South and north doesn't make any difference in these volumes. So, but we want to go to volume 2. That way, here's the actual tables. Notice there is a limitation to using the 249 tables, and that is any declination of the celestial object that you're taking a sight on. If it's greater than 29 degrees, you can't use these tables. You have to go to either publication 229 or a different method, like the law of cosines method, where you use just the trigonometric formula. Anyway, for this example, we're at declination 20, so we can use this table. So we're going to zip on down to the actual pages that we need to get the information from. There's a lot of information on the front of these volumes. You can read them if you want to. You don't have to. A lot of details on explaining exactly how you use them. There are also some auxiliary tables on the front section of this volume. Here's table 1, which we don't need. Table 2, we don't need. Table 3 we don't need. Table 4 we don't need. Now table 5, I'm just showing you where it's located. Table 5 is right here. And then we will be using this to make a correction from our tabulated altitude to account for a difference in minutes of declination. So we're going to be using that. I'm just showing you where it is in this volume. So now let's go on down to where we have the actual pages that we're looking for. And we're looking for latitude 5. You want to enter the tables based on the latitude, and we're at latitude 5. Again, it's south or north, doesn't make any difference. Just look for the pages that say 5, and you'll see it up on the right-hand corner or the bottom left-hand corner. That's table, or that's latitude 0. We got to keep going down to latitude 5. Okay, we're at latitude 2. We got to keep going. There's 3, 4. Okay, here comes 4. Keep scrolling down to latitude. Here's latitude 5. So we want to see, here's latitude 5. Now that says contrary to the declination, so we don't want that. Remember, our problem said same. So we want to go down to where it's the same. And here's the right interval, 15 to 29. And here's 20 degrees declination, same, and make sure we're still on latitude 5, which we are. Okay, so this is the page we want to use to get our information. So each column has the calculated altitude, a difference in altitude between 19 degrees and 20 degrees of declination, and then the relative azimuth, Z. So this is the page we want. So I'm going to copy this page, and we're going to go back to our worksheet, and I will present the page. Here's the page. And again, here's the information that we enter this page with. Latitude 5 degrees, declination 20, and LHA 32. Latitude 5, same. I forgot to mention same, and it is the same, so that's good. Here's our column of 20 degrees, and then our row of 32 LHA. So here's the column, there's the row. Where they intersect right there is the information that we want to take. Make that a little bit bigger so we can read it. So basically that says 55 degrees 27 minutes in HC, that's our calculated altitude, minus 22 is the difference between this altitude in declination 20 degrees and this altitude in declination 21 degrees. If you subtract 22 from this value, you'll get this value. It's just that simple. So we want to take this information back to the worksheet and just put it in this first line here. 55 degrees, 27 minutes. Difference in altitude is negative 22 minutes. And our Z, our relative azimuth, is 61 degrees. So we're almost done. That's all we had to do is take these numbers out of the publication 249. However, these values pertain to a declination of 20 degrees. We have a declination of 20 degrees, 21.9 minutes. These 21.9 minutes are sort of hanging out here. We have to account for them to make sure we have a precise location. So we're going to take the 21.9 minutes and stick it over here in this box. So now we basically have to find out what percent of the 22 minutes of increased altitude between for 1 degree of altitude does the 21.9 minutes represent. That's when we go back to the table, to table 5, which is this. Here's our information. 22 is in this top row. Doesn't make any difference whether it's positive or minus. It's just an interpolative value. And then here's the 21.9. It's not broken down to tenths. It's just whole numbers, 21 to 22. And when we come to this intersection, which is right here, 8 is our correction to account for those 21.9 minutes of declination. So we're going to take that back to the worksheet. We're going to put the 8 minutes and match the sign. Could be positive, could be negative. Make sure they're the same. And then you just subtract. That's the correction to our tabulated altitude, which brings it down to 55 degrees, 19 minutes. Now we take that, we simply add that in box or block 5, bring down our HO from our entry data, 55, 5.8. The difference is our intercept, and the rule is, remember, ho, mo, to. If HO is more than HC, you'd move the DR position toward the GP. If it's less than HC, then you'd move it away, which means the opposite direction of our ZN. In this case, HO is less than HC, so you would move it away. Now we want to calculate what the ZN is, which is this block right here. So if LHA is less than 180, which it is, it's 32 degrees, we're in this column. Now we're in the southern hemisphere, which is going to be down in this column, or this row. So it intersects right there. So basically we add Z plus 180. Z is 61 degrees plus 180 is 241 degrees. The intercept is 13.2 nautical miles. Again, it's away. So let's see how this looks when we plot. So I've actually plotted 2 ways. I've actually plotted based on what we just calculated with our 249 worksheet tables and our intercept of 13.2 and 241 degrees for our ZN away. So which means here, the ZN is the arrows, and we want to plot it the opposite direction, which is away from that, by the length of the intercept, 13.2. And that gives us an EP right there. And so this is our line of position. We do the same thing with the LSC worksheet. But LSC worksheet, this is important. We don't plot from an AP because we don't have an AP down here. We plot from the DR. And this is where we use it's more specific because this is where we use the actual trigonometric formula. So we don't really have to deal with the tables and then entering in whole numbers. We can use the exact DR with the minutes because we're plugging that into the equations. So that's going to give us a different intercept should be the same azimuth, which it is, but just a different intercept of distance. So it's 29.2 away. And lo and behold, we end up on the same LOP. So this indicates that this is great. Now, it's not probably prudent to change the position of your DR on your nautical chart based on just one sight reduction, because you could be anywhere on this line of position. Same thing with this method, anywhere on this line of position. So that's why it's important to whichever method you use, you should select at least 2 celestial bodies that are available at the same time. And I'm saying probably within 20 minutes. If you can take 2 or 3, ideally, different celestial bodies within a 20-minute period and plot them all from the same DR, you're going to get an intersection of LOPs, and that's going to be a good solid celestial fix with whichever method you use. So I hope that that helps. Hope you can understand how you use that table. It's very easy. And thanks for checking it out. And I'll see you next time in the next lesson.